Have you ever felt that someone is your soulmate, your other half? Well, guess what? Quantum particles feel the same way. To understand how these particles interact, we will first look at the classical system. We have two objects we will call ceons. The C stands for classical. To make it easier to understand, we will think of these ceons as cakes. These cakes come in circles and squares. The cakes are independent if knowledge of the state of one does not give useful information of the state of the other. This table shows the probability of the shape of two independent cakes. There is an equal probability of either system having either shape. Entangled cakes will be the same shape as one another. There is a 50% chance they will both be circles and a 50% chance they will both be squares. Now switching from the classical system to quantum theory. First, there are two things that quantum theory forces us to accept as fact. 1. A property that is not measured does not need to exist. And 2. Measurement is an active process that alters the system being measured. Now let's get an idea of how small quantum particles really are. The word quantum refers to the smallest amount of something you can have. You can't break a quantum of something down because it is the most basic building block. These particles are subatomic, smaller than atoms, which makes them harder to study and understand. For example, if we compared an atom to a quantum particle, the atom would be like a football field, and the particle would be as small as a box of cereal. So, quantum particles work basically the same way that the cakes do, at least until we add another element. For example, if we look at shapes and colors, circle, square, red, and blue. In the classical system, this implies 4 possible states: red circle, red square, blue square. However, according to quantum theory, the object having the option of different shapes and colors does not mean it possesses both a shape and a color at the same time. It could be a circle, a square, red, or blue. This definitely goes against Einstein's theory of common sense. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen did an experiment of quantum mechanics. They took a pair of entangled gluons. Of each, they were able to measure shape or color, but not both simultaneously. When the shape or color was measured, the results always agreed. According to quantum theory, this would happen even over a great distance. If the shape of one and the color of the other were measured, there was no correlation. Measurement in one location seems to affect the state of the system in another location. Einstein called this spooky action at a distance. After this, nobody really believed that quantum theory was real or provable until the 1960s, when John Bell theorized hidden variables that we haven't discovered yet. He thought if we understood them, they would no longer be spooky. In his experiment, he had 3 assumptions. If followed, would prove the classical system, and that hidden variables create the illusion of quantum entanglement. His 3 assumptions were: first, freedom of choice. Physicists can make measurements freely and without influence from hidden variables. Second, locality. Nothing can influence something far enough away that a signal between them would need to travel faster than the speed of light. And last, realism. Objects have properties that they maintain whether or not they are being observed. Other experiments have shown physicists can measure spin, momentum, or polarization. When particles are entangled, the results of these measurements are more statistically correlated than the classical system would expect. Once we understand this better, there are tons of applications for it. A group of researchers created an atomic clock that only loses 1 second every 50 billion years. We can also make unhackable codes, super powerful computers called quantum computers, and there is also a theory that says birds use quantum entanglement as a sort of biological compass to stay on track. So far, we understand how to study and control quantum particles, but do not understand why they happen or what it means for the nature of reality.